Okay, today we're going to begin our discussion of cohomology. This will be the first in a series of lectures on cohomology, which will complete the course for us. So first, let me remind you about homology. So we've been discussing homology the last several lectures, where homology just begins with some chain complex. And so you have some chains of the form, whatever they might be, C3, C2, C1, C0, 0, and so forth, as long of a chain complex as you like, where these are all abelian groups, right, of CK is an abelian group. So let's do a concrete example. So you might have something like Z, 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 and maps in between them. And let's just say it's 0 here and onwards. It could be more, but let's just say that it's 0. So we have these maps between these guys. And these maps we often think of as our boundary maps. Where, of course, this last one would just be the 0 map. So in our example, this, of course, is just setting it to 0. That's just setting it to 0. We could make these also 0 maps. Let's make this something else. Let's make it like the times 2 map. Okay, so let's put 2 there for times 2. So what that means is here, this sends the generator 1 to 2, and more generally, the element n gets sent to 2n, right? But here, everything just gets sent to 0. Here, everything gets sent to 0. Then we defined homology to be Hn of the chain complex is just the kernel of the, so if there's like C2 would be the kernel of this map, the nth map over the image of this map, over the image of boundary 3, or boundary in this case, n plus 1. This image is contained in here because one of the properties of this sequence is, in order for the sequences to be well defined, is we insist that this composition gives you 0. So in general, this composition should be 0 for this to be a chain complex. And so you get that this image is inside of this kernel, and since it's abelian, this is now a well-defined quotient. So we can define our homology groups this way. And so we can go ahead and actually calculate the homology groups for this example. H0 of the chain complex would be the kernel of this map, which is Z, mod out by the image of this, which is mod out by 0, so it's just C. H1 of C would be the kernel of this map, which is all of Z, mod out by the image of this map. Well, what is the image of this map going to be? 2Z, right? Everything gets sent to 2 times it, so it's the even integers. So 2Z, which when you do Z mod out by 2Z, it's the group Z sub 2 we denoted, the cyclic group with 2 elements. H2 of C would be, now we're on this guy. So what is the kernel of this map? Well, the only thing that gets sent to 0 is 0. So this kernel is trivial. So already this group is trivial, right? And finally, H3 of C is the kernel of this map is all of Z, mod out by 0, so it's Z. And anything higher would be 0. Anything higher. If you have H of any n greater than or equal to 4 of C, that would just be 0 as well. Okay, so that's your homology. What is cohomology? So we want to now talk about cohomology. So what's cohomology? For cohomology, we are going to dualize our chain complex by applying Hom of whatever the chain is to Z. So what you're going to end up with is each of these guys are going to be replaced, like your C3 will be homomorphisms from C3 to Z. Or C2 will be homomorphisms from C2 to Z. Or C1, homomorphisms from C1 to Z. Homomorphisms from C0 to Z. And, well, homomorphisms that begin off at 0 will still be 0, so that's still 0. I started getting excited dualizing, and I made a fatal error. So what's my mistake? Yeah, so my arrows need to be switched. So let's talk about why that is. Okay, first of all, are we clear what these groups Hom are? So this is the set, so if this is G, if this is some G, this is just all homomorphisms. This is the group of homomorphisms. So this is itself becomes a group. Because if you have two homomorphisms, you can combine them and get another homomorphism, right? So this is the group of homomorphisms, there we go. Homomorphisms. You can think of like some homomorphism F from G to Z. Okay? Group of homomorphisms. So let's think what happens really fast. Like if I have some homomorphism, so let me just do something more general over here. If I had some like G mapping to some H, but now I want to think of Hom. So now I want to come over here and think of like Hom of G to Z and Hom of H to Z. If I have something in here, Hom of H to Z, I can think of it as some map F from H to Z. So this is not the same yellow as that yellow. So here I have some map F from H to Z. And maybe I'm given some map from G to H. So I'll call this map little g. Now, how can I get a map from G to Z? Well, the map from G to Z that I can get would just be the composition of these two maps. It'll be just G composed with F. So first you do G, then you do F, right? So you should think, I had a map from G to H, but what it ends up doing is becoming a map that sends homomorphisms from H to Z, homomorphisms like F, to things like F, will now get sent to things like F composed with G. Because that is now a map from G to Z. From G to Z. So, a lot of errors going on here. So when I have a map from G to H and I dualize, G ends up inducing some map here where G star of F is just F composed with G. Happy with that? So that's why here all these arrows are going to get flipped. All of these arrows are going to get flipped. And so instead of having boundary 1, 2, and 3, this would be the map induced by boundary 1, the map induced by boundary 2, and the map induced by boundary 3, where what that map does is it just takes this homomorphism and composes it with the boundary map. Okay. This before was just the map that sent everything to 0. You should think if you compose with a map that sends everything to 0, it's still saying everything is 0, because homomorphisms have to send 0 to 0. So if it was 0 before, it's still going to be 0 afterwards, after dualizing. So let's think about what that means for our example. So in this particular example, we had all of these chain groups were just Z. The first C0 through C3 at least were Z. So these all become Hom of Z to Z. Hom of Z to Z. Hom of Z to Z. And Hom of Z to Z. And 0 to the left still. Because if it was 0 here, you look at homomorphisms from 0 to Z, well, there's nothing. There's just has n 0 to 0. That's all I can do. Okay. And we just said, if the map was 0 before, it's 0 afterwards. So these are both 0. And this is the one that's going to be induced by the times 2 map, which means you're going to compose with times n by 2. So we'll come back and think about this one more in a second. But first, let's think a little bit about what is Hom of Z to Z. What are homomorphisms from Z to Z? So like down here, what is Hom of Z to Z? Well, let's think. I have to think of all homomorphisms from Z to Z. It's a homomorphism. So once I know what it does to the generator, I know what it does to everything. So to define a homomorphism F from Z to Z will be characterized by what F does to 1, right? And where could F possibly send 1? Wherever you want. So F1 can go anywhere, to any n in Z, right? So you can think like there's an F that corresponds to each value of Z. F1 would just send 1 to 1, F17 sends 1 to 17, F negative 314 sends 1 to negative 314, right? And so that shows you then, and then you can compose these Fs. And if you compose like an F2 with an F3, you get a F.
It would be added homomorphisms, not.
Yes, I'm sorry, I'm speaking loosely. If you add 2 homomorphisms, so if it's like F2 plus F3 of 1 would be F2 of 1 plus F3 of 1 would be 2 plus 3, which is 5, which is F5 of 1. Right, so that's what I have in mind here. So that shows then that Hom of ZZ is isomorphic to just a copy of Z. Happy? So each of these you can think of as being isomorphic to just a copy of Z. Now, all of these 0 maps are clear, they're just 0 maps. But let's take a second to think about this middle map. It's not surprising what it's going to do, but let's just convince ourselves of it really fast. So here, I have some F from Z to Z. So maybe I have something like, some Fn, right? So that's the one that's going to send 1 to n. And I'm going to compose it, I'm going to apply this map induced by 2 to it. This map induced by 2 on Fn. So what would that be? Well, we said here it should be Fn composed with the times 2 map. So if you start out with 1, you times it by 2, it's now 2. And where would 2 get sent to under Fn? To 2n. So this is the same, 1 is getting sent to 2n, so this is F of 2n. So Fn gets sent to F of 2n. Fn gets sent to f of 2n. And so if Fn we're thinking of as being identified with n, f of 2n is identified with 2n, then this map here, 2, the map induced by 2, will correspond to, again, the times 2 map. Okay, great. So now we have this dualization. Here this was called a chain complex. This is called a cochain complex. These maps are called coboundary maps. Okay, everything's the same as it was before. You just add co at the beginning of it, right? So it's like some, I don't know, hipster establishment. It was like the co-op or whatever. I don't know, they put co's in front of things because we all live in harmony and we cooperate. Great. Okay. So these all have co's in front of everything. So what is the cohomology then? So the way we'll denote the cohomology groups of this guy, I'm going to erase this. We know now that this is Z. So what are my cohomology groups? I'll denote it H upper 0, and then I'll put here my chain complex, and I'll keep track that I dualized it using Z. What is this first one going to be? Well, you just take the homology of this cochain complex. You do it the same way. So in general, this Hn will be defined by the, oh, well, let's be careful. If we're doing like Hn, like imagine we're like here. Just like before, it's going to be kernel over image. But now it's kernel of, notice, it's kernel of the coboundary map n plus 1 over the image of the coboundary map n. Whereas here, it was the kernel of the boundary map n over the image of n plus 1, because the arrows got flipped. So you got to be careful with your indexing. So here's our general formula for cohomology, and now we can quickly calculate. C0 of this guy comes out to be what? H0 of this is just going to be the kernel, which is the whole thing, so Z, over the image, which is 0. How about here? What is H1 of CZ? The kernel is 0, so now this is 0. H2 of CZ. The kernel is Z over the image, which is 2Z. So this becomes Z mod 2Z. And then finally, H3, the kernel is all of Z over the image, so it's just Z. So H3 is Z. And notice it is not the same as here. Here, your homology, H1 was Z2, and your homology H2 was 0. Here, your first cohomology group is 0, whereas the second one is Z2. So these got flipped precisely because these arrows got flipped. Is that good? Okay, very good. So let's think a little bit about the relationship between homology and cohomology. So how are these guys related to each other? So naively, your first instinct might be that Hn of, say, some chain complex with Z coefficients can just, maybe it's just isomorphic to, maybe there's some way of mapping it onto the group of homomorphisms from the homology of C to Z. And we're going to see, yes, indeed, there is a map here, but it's not an isomorphism. I mean, you already know it's not an isomorphism. Just look at like H2. H2 is Z2, but over here, you know, this is going to be 0. Even when you look at the Hom of this with Z, it's still 0. So this isn't going to work. But I mean, it kind of makes sense. Like, I don't know. This is like trying to dualize the homology after you've calculated it. Well, this was dualizing first the chain complex, then calculating the homology to get the cohomology. So it kind of makes sense to compare these, right? Okay, so let's just think carefully about what this is again. This here is we wrote it down right here, the kernel of the nth plus 1 coboundary map. Sometimes I'll get tired of writing this as the dualization of this boundary map. And so sometimes I'll introduce a new notation. We'll just call it delta 1. And I'll just call this delta 2, and this delta 3, and so forth. So to make clear, maybe I'll just do that now. I'll call that delta n plus 1 over the image of delta n. So let's say we have some element of this group. So what might that look like? Yeah. So let's say we have some element of this group. Well, first of all, these guys live in whatever your Hn is. So this guy himself is a homomorphism from Cn to Z. This guy is a homomorphism. Phi is a homomorphism from Cn to Z. But it's in the kernel. So what does it mean to be in the kernel? That means end delta of n plus 1 of phi should be 0. But we said what this means is it means that phi of composed with partial of n plus 1 is 0. So that's saying phi of anything in the image of this map will give you 0. Right? That's what this means. Okay. So I'm just unpacking what it means to be an element here. But since this is a homomorphism from Cn to Z, we can think that this induces a homomorphism from Hn of C to Z. Because what is Hn of C? We call this Hn of C is just the kernel of the nth boundary map over the image of n minus 1. Did I get those indexes right? I think so. No, image of n plus 1. It's important. But something in here is something that's in Cn. So if you're in here, you're in Cn. This is a subset of Cn. This kernel, so this kernel of boundary n is a subset of Cn. Right, like come back over here. If you're in the kernel of like the second guy, you're a subset. You're living inside of C2, right? If you're in the kernel of the third boundary map, you're living in C3. So if you have something in here, you can think a representative is a subset of Cn. We'll have to think about this modding out in a second. But right now, just, if you're in the kernel, you're in Cn. So you can think of phi. So what we'll do with our phi is I'm going to define phi 0 to be phi, which is a map from Cn, just restricted to the kernel of partial n. So now this is just a map from the kernel of partial n, which is a subset of Cn, into Z. So I've just restricted this map to just the kernel. And I'm giving it the name phi 0 to distinguish, to make clear that I've restricted it. Now, what I want to argue is that this map induces a map on the quotient. But in order for this map to be a map on the quotient, we need to make sure that this map sends everything that in the what you quotient out by to 0. But that's already satisfied right here. We already showed this. So precisely because we've already shown phi sends the image to 0, and so does phi 0. Yeah, this is also true for phi 0, because that's just restricted to the kernel, which this is a subset of. You can then just define the induced map on the quotient, where you just see, okay, take some representative, map it over, because it's going to send everything in the image to 0. So we're good. So this now is just a map now from Hn of C to Z. And so in some sense, you could think like this map is just going to himself, except, you know, really it's the map that's restricted to the kernel, then induced onto the quotient, right? So that's what this map does. It sends phi to the induced map on the quotient. And that makes sense because it satisfies this property. So there's a nice map H here that does this. Okay. Well, we've already seen this is not an isomorphism. It is a homomorphism. It's not too hard to check that this is, I mean, it's like you're not changing these things. It's the same map, it's just the induced map on the quotient. So this is a homomorphism. But we've already seen from our example, this won't be an isomorphism. So a natural question to ask then is, what is the kernel of this map? What does the kernel of H become? Because once we know kernel of H, we get a nice exact sequence right here. This is just what's left over. Okay. So Hatcher spends a few pages going through and showing what the kernel is. I'm not going to do that. I'm just going to tell you. So here's the spoiler. This kernel comes out. This is our rapid fire cohomology. So we can go this quickly. Our kernel comes out to just be Tn minus 1, which is the torsion subgroup of Hn minus 1 of C. So this is some subgroup of Hn minus 1 of C. So by torsion, I mean non-free part. So torsion is the way we say non-free. So let me just give you a quick example. If you have some Hn that's like, so if you have some group that's just like Z squared plus a copy of Z2 plus a copy of Z3, this Z2 is free. It's just a free abelian group generated by two elements. This stuff is called torsion. It's the non-free stuff. Okay. And so here, your kernel comes out exactly to be just the torsion, the Z2 or the Z3 component. Whereas, if we think about what Hom does over here, well, we've already said that Hom of like Z to Z is Z. But can you tell me what would be like Hom of Z2 to Z? Well, let's think. You have Z2, you have two elements, 0 and 1. Where can 1 get sent? Well, you're thinking of some map F. You're trying to think where F can send this guy. Keep in mind, F of 1, wherever it sends it, you need that F of 1 plus 1 to be F of 1 plus F of 1. And f of 1 plus 1, over here, 1 plus 1 is 0, because you're working in Z2. And since it's a homomorphism, it should come out to be 0. So f of 1 plus f of 1 has to come out to be 0. So what could f of 1 possibly be? Only 0 in Z, right? So there's actually only one map here. This has to send 1 to 0. And so this is 0. And there's nothing special about Z2. Any Zn has the same thing, because it's the exact same argument. Like if you're in Z3, you need f of 1 plus f of 1 plus f of 1 to be 0, right? If you're in Zn, you need n copies of f of 1 to be 0. And so Hom kills torsion, whereas it keeps the free part. You can check that if you have something like Hom, this isn't too hard to see, G plus H into Z, it's just going to be Hom of the G into Z direct sum the Hom of the H to Z. You put this all together, what you see what Hom does is it keeps the free parts and it kills the torsion. So this Hom kills torsion. And so what this Hom comes out to be the same thing as, well, let me get another color here. Here, this kernel came out to be Tn minus 1. What this Hom comes out to be is your Hn, but kill off the torsion. And so what you get then is you get this exact sequence where you have the torsion from the nth minus 1 homology group maps to the nth cohomology group, maps to the free part killing off the torsion of the nth homology group, maps to 0. Nice exact sequence, in fact, split exact sequence, from which we get that the nth cohomology group is just isomorphic to the free part of the nth homology group direct sum the torsion of the nth minus 1 homology group. Here's our result. Little like asterisk when C has abelian groups that are all finitely generated. This wave my hands here. I'm assuming this is finitely generated, but everything we're going to work with in this class is finitely generated. So let's see how this plays out over here. Like let's look at these examples. What would let's use this. So let's use this relationship that Hn of C of U complex with Z coefficients should just be whatever the nth homology was mod out by torsion, and then add back in the nth minus 1. Okay, so let's try and do this. So in this example, H0, we're just, okay, I'm getting lazy, just write H up to 0. What would H up to 0 come out to be? I'll just do it for CZ. What would it come out to be? Okay, well, there was no H negative 1, so that's just going to be trivial. But it'd be Hn mod out by torsion, that just leaves you with Z. So there was no torsion in H0. How about H upper 1 of CZ? These isomorphisms. H upper 1 of your, so the first cohomology group of your complex with Z coefficients. What? I'm saying Z coefficients, dualizing Homs to Z. What is this going to be? So Hn, so H1, mod out by the torsion, you have nothing left. So this first term is trivial. And then add to it the torsion from the previous guy. There was no torsion in that previous guy. So that's trivial. What did we get for H1 when we calculated it? We got 0. How about H2? H2 would be the free part mod out by torsion of H2. Well, H2 is just 0, so that's not very interesting. But then take the direct sum with the torsion of the previous guy, with your Z2 of that previous guy. So that just gives you a copy of Z2, which is exactly what we had gotten when we calculated out the cohomology, the second cohomology group. And finally, H3 of CZ is you mod out by torsion, it's already free, so you just leave that free part, Z, and you take the direct sum with the torsion of the previous guy. There is no torsion from the previous guy, so you just get Z, which is what we had calculated. Happy? So this is a really powerful result. Very powerful. Which means to calculate cohomology, you don't actually have to do this whole dual thing. We can just use this result. So, I don't know, should I do another example? Are we good with this? I mean, do you want to? Let's do a quick example. Okay. Feel like I'm kind of going to beat a dead horse. I don't know, I'm not going to do another example because it's pretty clear, right? Like, if you want to find the homology or cohomology of, find the cohomology of the Klein bottle, just do it, right? Klein bottle is the one that had a Z2 for H1, so it'll be very similar to what we did here. How about the cohomology for the torus? Well, for the torus, there is no torsion. So when there's no torsion, for the torus, it was just Z's and Z2s. It would just be the same as the homology, right? So, it's only when you have torsion that things get changed between the homology and the cohomology. So nice, powerful result. Okay. So you might think then, like, well, what's the point of cohomology if it just reduces down to homology? It's a good question. Well, one thing we can do with cohomology is instead of dualizing with Z, we could dualize with some other group. This doesn't have to be Z. This could be whatever group you want. And now I'm kind of feeling bad I used a G here. So let me instead change that to H, because I want to dualize with respect to some group G. So I'm going to change this to some other group G. So what we do is we would just do hom for that G. So let's do an example of this. So the first one was this case where G was Z, but we could pick a different G. And your choice of G is called the coefficients of your homology groups. So a few times I've already slipped up saying Z coefficients. I just meant I was dualizing with respect to Z. But now we can dualize with respect to something else. So give me your other favorite group. What group should we dualize with respect to? Z2, great choice. Okay, it doesn't have to be Z2, it can be whatever, but why not Z2? So let's just like see how this works out. So here we would be, okay, I don't want to rewrite this whole thing all over again. So I think what I'm going to do is I'm just going to change this to a Z2 and change all of these to Z2s. And now let's do an orange. Let's think about what we get for our particular example. Let's just keep it yellow. Let's just modify this example. 2, Z2, Z2, Z2. What is hom from Z to Z2? It's not 0. 0 is if it was from Z to Z. But what is hom from Z to Z2? So maybe I should come over here. We should think about this for a second. What is hom from Z to Z2? Homomorphisms, well, it's going to be defined, characterized by where it sends the generator, 1. So where could 1 get sent to? Well, 1 could get sent to 0 or 1, right? You could have some f0 that sends 1 to 0, or you can have some f1 that sends 1 to 1. And those are both homomorphisms, right? So you have two homomorphisms. So this is a group with two elements. This itself just comes out to be Z2. In general, Hom from Z to G is just isomorphic to G, because each map is characterized just by where it sends 1. So if you know where 1 gets sent, then you know you have a homomorphism for each element of G, so this is isomorphic to G. Okay, so these are all now Z2s. The 0 maps are still 0, but what does this induced map by 2 do? We said it's composition with 2, so it's going to send Fn to f of 2n. So it'll send f0 to f0 and f1 to f2, which is f0. So it sends them both to f0. So what is this map actually? It's the 0 map. So now by doing Z2 coefficients, these are all 0 maps, right? Which means that my Hn of this particular chain complex with Z2 coefficients are all just going to come out to be Z2, because each one of these is the kernel of the image, which is Z2, Z2, Z2. These are all Z2 for n equal to 0, 1, 2, 3. 0, 1, 2, 3, and 0 otherwise. Is that good? Okay. So different homology because we're using different cohomology because we use different coefficients. We dualized it differently. We could do several more examples here of this. But hopefully you get the idea of how this works. So this whole thing is no longer going to hold up. Because here, I no longer have Z, but now I want to update this. So let's modify this according to the discussion we just had. I no longer want these to be Z's, but I want them to be G's. Now, you still have this map H. It's just this guy is now, instead of mapping into Z, it's mapping into G. But this whole same argument holds up for this map G existing, this map H existing, this homomorphism H. So this still all makes sense. But no longer is this going to be related to homology in the same way as before. So this is no longer going to be true. This is no longer going to be true. So none of this is true anymore. So this special result we had before was just for Z coefficients. Now, in this more general setting, we instead get that this kernel comes out to be something called X of HG. X stands for extensions of H over G, extensions of H by G. So I'm going to tell you what X here is in a second. Where this X, it's going to generalize the idea of Tn, is X of n minus 1 of the coefficients of the chain complex within the group G. So this here, I mean, maybe this is a little messy. Let me clean this all up. What I'm trying to say is you just have a slightly more general thing here called X of Hn minus 1 of your chain complex, the group G. This is what's going to end up being. This is called the universal coefficient theorem. universal coefficient theorem for cohomology. Where, so what is X? What is X of like, well, let me just characterize X. If you have, so just like before, so the idea before was X, like here, that was just the torsion, right? X acts the same way, that if you have something that's free, it comes out to be 0. Whereas if you have something that has torsion, you're still going to get some kind of torsion. But it's not going to be just the Zn, because now you have some more general coefficients. So what you're going to get instead is G mod Ng. So like this is the generalization to new coefficients, right? So when your coefficients are Z, this is exactly like before, where this just comes out to be X of Z and Z would just come out to be the Zn. So it just keeps the torsion part. But your G could be some other group. Your G could be something else. Your G could be something like, I don't know, Z M, for example. Then X of Zn Zm comes out to be Zm mod out by n copies of Zm. Do you know what this is? Like those with some algebra background? What would this be? So maybe we should do like a quick little example of this. So a quick little example of this. Let's say I have like, you know, you tell me like Z6, let's say I want to calculate X of like Z6 and Z3. I think this is going to work. Is that the one I thought of the other night? Okay, I did a slightly different one, but this one should work too. So you might think, so here you're going to have Z6 mod out by 3 times Z6. So like, let's just think what this is. So what's in Z6? In Z6 you have 0, 1, 2, 3, 4, 5, right? And you're modding out, so it's the group of these elements. This is bad notation. you have these elements, right? And then what's 3 times Z6? It's 0, 3, 6, which is 0, times 3 gives you 9, which is 3, times 3 gives you 12, which is 0, times 3 gives you 15, which is 3. So what is this saying? This is saying, like modding out by this, you really just mod out by 0 and 3. So this is really just 0 and 3. Right, so 0 and 3. It's just setting 0 equivalent to 3. So you're thinking of 0 and 3 as being identified with each other. But if 0 and 3 have been identified, then 1 and 4 have also been identified, and 2 and 5 have been identified as well. So what is this group? What? There's 3 elements, 0, 1, and 2. It's Z3. This just comes out to be Z3. So maybe it's not obvious like what it is in general. I'll give you the spoiler. This just comes out to be Z of the greatest common divisor of M and N. So this is a little fun algebra problem if you think about why this is true. But hopefully this gives you some insight to that. So what X does is it kills the free part, but then it like puts torsion onto G, whatever the G is. So it's not necessarily just Zn, it's because you could have some other coefficients. And X, just like these other guys, has the property that X of, you know, like H1 direct sum H2 with G is just X of the H1 with G direct sum X of the H2 with G. So you can just do one piece at a time. So you just kill off all the free stuff and then use all the torsion to figure out what it is in terms of the new G coefficients. Okay, so I wanted you to see this universal coefficient theorem, but oftentimes we'll just be using Z coefficients. So typically our coefficients will just be over Z, and when that's the case, we'll use this special form of it, right? So in practice, we'll typically use this, but sometimes you might be working with like Z2 coefficients or Z3 coefficients, in which case this would be the more general form that you would follow. So you still can calculate cohomology in terms of homology. Once you know your homology groups, you do a little bit of algebra, you can deduce your cohomology. So in terms of just what the actual groups are, there's no new information from cohomology. Because the values of each group are determined by the values of the groups of the homology groups, right? So you might think that this whole exercise in cohomology is nothing new. And in fact, it turns out to be quite similar. That what you can do is you can go through and you can define, you can define singular cohomology, just like we did with groups. You just dualize the chain complex. You can define simplicial. You can define cellular. And you show that all of those cohomology theories are the same, just like we did for homology. So everything falls out the same. And all the results for homology have analogies in cohomology. So, excision, Meyer via torus, like all of this. All of this is exactly the same in cohomology. It's just the arrows get flipped. So, Meyer via torus looks exactly the same, but the arrows are going the opposite way. And so, I'm not going to spend a lecture on this. We have limited time left in the semester, but I'm just saying everything works out the same in cohomology as it did in homology. Just things have flipped backwards. And so, at the end of this lecture, you should think cohomology is pretty useless. It tells you nothing new. Just looking at what the groups themselves are, that's true. Because the groups themselves are determined by the groups of homology. But it turns out that cohomology gives rise to a particular structure with something called the cup product that doesn't exist in homology. And so next lecture, we'll get into the cup product and show you what is this new structure that arises in cohomology, structure between the groups that doesn't exist in homology. And so cohomology allows us to see a higher level of structure. But that'll be next lecture, so that's where we're headed. Okay, we'll stop there.